we're going to be talking about some basics principles of interfacing. We'll look at how microprocessors interface with other components. We're going to be looking at I/O addressing, interrupts, and direct memory access. So the interrupts are the ones that we talked about last time, but here I want to show you another way to understand interrupts using animations. And also for the case of direct memory accesses, we will show you a animation to illustrate how it actually works. And then we're going to be looking into some of the topics related to interfaces and buses, such as arbitration, hierarchical buses, and we will again review some of the protocols, although not going to be going into very detail of these individual protocols. So if you think about an embedded system, it has a few functionalities. Processing is the core function for an embedded system. It is supposed to process data and generate some of actions. Processing includes transformation of data, and these are all implemented using processors and algorithms. The other part of the embedded system is the storage. The storage is used for retention of data, and it's implemented using memory. And there's the other part of the storage, sometimes called secondary storage. It's used as a storage device that's intended to store the data for longer duration, especially when the system is offline. When we use memory, the purpose is to retain the data for the duration when the processor is alive, is executing instructions, performing these processing tasks. The third function is communication. Communication is to transfer data between the processor and memory and also other components. This communication or data transfer is implemented using buses, and we call this as interfacing. Let's start with a simple concept, bus. So what is a bus? Before we explain bus, we need to understand that for components to talk to each other, they have to be connected through wires. Wires are conductors, and wires can be unidirectional or bidirectional transferring data, but most of the time it's bidirectional. And one line may represent multiple wires. So what we mean here is, so as we see on the right side, this picture, we have processor, we have memory, and we have these lines connecting these two components. And on these lines, we see arrows indicating the direction of the signal transfer. And also we see labels indicating their functionalities. So the first one you see here is a wire coming from processor to memory, and we see only unidirection arrow here, and also the label is RD prime WR. So this wire is a unidirectional signal that comes from the processor, goes to memory, and this is a control signal, and this signal is to indicate this is a read operation or write operation. Bus is a set of wires with a single function. We can have address bus, which is used for transferring addresses, and also we see data bus. In this case, we have both address bus and data bus. And for the address, as you can see, it's one directional or unidirectional, and it carries a number of signals. And to be specific, we have 12-bit address. And on the other hand, we have a data wire here, and this line here is bidirectional, okay? And we have 8-bit data. So these data bus, address bus, well actually address bus and data bus, these two buses, each of them consists of a bunch of wires, and these wires transfer signals, and these signals could be used as address or data, depends on the design. So in general, you will find these collections of wires or buses that carries address, data, or control. And for the components to work, we need to follow specific protocols, and that is the rules for communication. Ports is the way we describe the connectors on the processors, and it's it's at the periphery of the device or the processor. It is for connecting a bus to the processor or to memory or to other components. We often refer these ports as pins, and the actual pins on the periphery of the IC package can be plugged into a socket or soldered into a PCB, printed circuit board. And sometimes these, physically, they are not pins, they are metallic balls. So these can be also soldered into a PCB. And you often find these, physical form can be not only in the, pins, and also you can see pads also used for carrying out larger current. Single wire or set of wires with single function, these are what we often call a port in the context of a processor. So as we see here, this will be an example of address port, and this will be a data port. Timing diagrams. You will see a lot of timing diagrams when you look into the data sheet of a device or a controller that you want to use. These timing diagrams are used for describing a communication protocol. And the way we read or understand such timing diagrams is to look at the diagram from left to right. Imagine that you have a time axis on the horizontal direction and goes from the left to the right. So time goes this way. And you find different signals. Some of them are control signals, and some of them are address or data signals. In this example, you see here we have two control signals. This is read-write control, and this is enable. And for the control signals, you often see these are this is a single line, and you see this line be going stay at low or going to high. Like in this example, enable, you stay at low, and then it the pulse the voltage is raised to high at some point, and lowered to low level. For other signals like address and data, you see a single line branch out to two lines. Like here for the data, you see the same case, start with a single line and branch out to two lines. The way to understand this is that because oftentimes for address and data, you're not talking about a single wire. So it actually consists of multiple signals. So for address, you may have 12 address bits. For data, you may have 8 data bits. So that's why it will be impossible to represent the actual values using just one single line. You will see that this single line here branch out to two lines. This is an indication that the address will become valid. So this is a transition from invalid status to valid status. And of course, this is the duration of such transition process. And the reason we indicate the signal as valid by using these two lines, because for let's say 12-bit of address, some bits are 0, some bits are 1. So it would be impossible to really write down a value here. But with these two lines in parallel, we know that you expect the signal, the values on the address bus become valid. Same case for the data. Now we start with some garbage data, but at some point the data will be present on the data bus. So you have the actual value on the data bus, and these will be kept valid for a certain period of time. So what this read protocol is trying to describe, if you want to read, because this is a read prime or read bar, this is indicating that read is active low. So when you have a 0 voltage or low, logic 0, and that's the indication of we're doing a read operation. And when you see enable going from 0 to 1, that is to enable the read. So we're going to read the actual data. And for this particular design, we use memory address or some sort of address to read the data. So that's why we need the address to be valid before we raise the enable signal from low to high. That's why you see the address signal is actually becoming valid long before the enable signal changing from 0 to 1. And this time, you often see arrow or double-sided arrow between this line and this line. That's to indicate this is the setup time. So that's the time we have to have in order for the read to happen properly. And that means the address signal have to become valid for at least this long before we raise the enable signal from 0 to 1. And after that, you see this kind of a connection. This is an indication that when enable is raised to high, that means the microprocessor or the controller is trying to read data by using this address. And the data is not valid or available until this T read time. That's why you see such a delay between the moment the enable becomes 1 and the moment that data value is valid on the data bus, and that's the T read. Now these labels may be different, but majority of the timing diagrams follow such convention. So a single line indicating it's a control signal or single value, single wire, with this two lines in parallel indicating that this is the bus, which consists of multiple signals. Protocols may have sub-protocols, bus cycles for read and write. As you can see, this is a read protocol, this is a write protocol, and they behave differently.